So today's class we are going to just start something discussion about orthogonality. Orthogonality. You might have some idea of orthogonality from the understanding of how we study dot products of vectors. Given vector may be orthogonal to another vector. The intuition is basically the same, but the thing is that here we are going to have that very thing in the context of how we study this finite dimensional vector spaces and how we constructed various spaces and those in those spaces, those bases, some of which can be orthogonal or orthonormal if they are not orthogonal. So if they are orthogonal, first let me try to define orthogonality. 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 So orthogonality. So the important thing which we normally mention is that our intuition was basically R2 space, means two-dimensional space. The intuition becomes more, but we can extend it to Rn. When we in the beginning of the class we started that we can in principle go for R2, 3, 4 and higher dimensional spaces. But the intuition, geometric intuition becomes pronounced in R2, so that this exemplifies our thing which we are more interested in that sense. And we have been normally we have qualitatively dealt with things. Now in orthogonality as an idea, we can quantitatively compute some quantities. The way once we would have a dot product of two vectors, we have not only qualitative, we have a quantitative account of things, how the components vary, where normally you would say, for example, E dot B is modulus of B into cos of theta. So this modulus is sort of also magnitude is also involved. So in this sense, we can say that if we, for example, if we for the sake of generality, not only R2. So how should we proceed? So if we start with the R2, and if X is these are two, and Y we define like this in terms of the way we have defined X and Y in terms of zetas and datas. So the distance formula usually between the two can be zeta 1 square minus zeta 1 square plus zeta 2 square minus zeta 2 square. Or conventionally, if you want to have this mod of this, it will be equivalent to root of zeta 1 square plus zeta 2 square. And similarly, mod of y will be zeta 1 square plus zeta 2 square. So if the distance is from the origin, then it will be 0, 0. So distance between the two, it will be x minus y. So if it's from the origin, so it will also be 0, and accordingly. Now, if we want to see it here, for example, if alpha is angle between segments 0 to x along the positive axis zeta 1, and beta is the angle between segment 0 to y along the positive axis beta 1, then So the angle between the two vectors, alpha minus beta, and the cosine will be. So for example, if it will be normally modulus of x, modulus of y into cos of alpha beta. You can write it. So it will be in that sense. We can say it will be in that sense. It can be cos of alpha beta. So x, y, you can write it as zeta 1 plus zeta 2 divided by modulus of x, modulus of y. Or if we want to write this zeta 1 plus zeta 2 as x of y, and x is zeta 1, zeta 2, y is neta 1, neta 2. So the simplest expressions of zeta 1, neta 1 plus zeta 2 as a product of x and y, it's orthogonal. It's zeta 1, neta 1, zeta 2, neta 2. It will be like this. If you want to have the angle between them, we can write this expression like this. You can write it like that. So now the point is, for example, the angle between if it's cos of if this angle will be cos of alpha minus beta. So if you want to write as the angle, so it will be sort of cos of alpha minus beta, and the difference of two angles between these alpha and beta, which is sort of defined by how we define x and y, and how they are the angles which are subtended between, how we can measure the cos angle between the two. So alpha and beta can be written as cos alpha cos beta minus sin alpha sin beta. So it will be equivalent to product of this and their modulus x and y. This. So you can also basically this is extended form of this. So you can start from this and you can just have a justification for this thing. And the distance from 0 to x, if it's from origin, so from it's like modulus of x is equal to xx. From x to y, its distance from x to y is x minus 1. And cos of angle between the two can be cos of angle between x and y. So it's not, we have written here x cos of alpha minus, you can see it's the cos of angle between the two will be, it will be this, how we define the product, divided by modulus of x and modulus of y. The way we in your earlier classes study scalar products or dot products of two vectors. Here or inner products is also another way. So, but if the inner product or the scalar product is between x and y, the angle between, if it's dot product, inner product in the same, its own vector, so it x dot x, it can be 0 or it can be pi or 2 pi, 3 pi, n pi, and so on and so forth. And the value of angle may vary from plus 1 to minus 1. So these are some facts. So the important thing is that we have to, it's simple product in R2. Now the point is the important thing is, or the interesting thing which comes later is that C2. If we replace R2 vis-a-vis C2 in the complex. How will these inner products, how they will pan out in some sense, and should it differ from the inner products, the way we define inner products for R space, R2 space. So if we, because the concept of imaginary numbers is involved, so the point is how we will see if we define this inner products for or C2, or how will this pan out. So in that sense, or we can say complex inner products. So again, we will define x in terms of zeta 1, zeta 2, and y in terms of zeta 1, zeta 2, and zetas and metas are complex numbers, and x, y can be written as product of x, zeta 1, zeta 1 plus zeta 2, zeta 2. But here so the expressions x and y can be measured, x and x, x and x, and x minus y can be used to sensible measures of distance. You can use them as sensible measures of distance. So since iota is equal to minus root of minus 1, so what modulus of iota x, what it will be? It is the inner product of this iota x, because it should be minus iota square will be minus, but since it's modulus, it will come out to be plus, so we can write it like this. Or further, if we just we can further write it as like this, or iota square x equal to minus iota square. So from this, what can we see? From this we say that iota, this x is positive if x is positive. It's x is positive distance from origin, and then iota x is not. So it's not, so iota x, so here if it's from origin, then it will be positive. But it's not from the origin, it's from the complex plane, if you remember. We have defined it in complex plane. So distance from iota x, distance from iota x, or from 0 or 0 to iota x is imaginary. So how we have to just have a remedy of this thing, that the modulus of this will not come out to be this positive, it will have something negative, and the negativity is because of that imaginary number which is associated with it. So the remedy comes in if we define it in terms of complex conjugate. If we define neta 1 and neta 2 in terms of not as simple complex numbers, one of them is complex, the other is conjugate of this. This is conjugate of this, such that their products a plus iota b into a minus iota b, it will be a square plus b square, or here zeta square plus eta square, zeta 2 plus. So if it's between x and x, If it's x and y, it will be so if x is y, so it will be for simplest cases x and x, zeta 1 will be zeta 1, zeta it will be like this, zeta 1 conjugate plus zeta 2 conjugate, it will come out to be zeta 1 square plus zeta 2 square. Is surely never, if you just go to the books, it will surely not be negative. So we define all the elements as a complex of this conjugate. That way we just do away with the minus factor which comes in. Now we are coming to our how we define inner product spaces. Inner product spaces. That will be inner product spaces. So inner product spaces again. What we are going to see. So now. So inner product spaces can be defined as, so if you have so inner product space definition. So an inner product real or complex vector space is a numerically valued function of ordered units x and y, such that x of y is y of x. So in a product space, we have only if we shift x to y, y to x, but as a complex conjugate, it should not. The property should not be different. If we flip one with the other, provided we have a complex conjugate of the same. The second property is alpha 1 x1 plus alpha 2 x2 into y. The product from our, if you remember our properties of the way we define vector spaces. So, but here it's complex spaces, so you can say, so these are complex spaces, the properties should be x1y plus alpha 2 x2y. Third, the self conjugate. If you have this self conjugate of this, it should always be either if x is 0, then it will be 0. Or if it's not 0, it will be always positive. It will be positive or it will be 0. If x is 0, if x is 0. So an inner product space is a vector space. This is called inner product space. With inner product. With inner product. One second. With inner product. So in a real vector space, conjugation one meeting. In real or complex implies that x and x is always real, and inequality makes some sense. That's it. Such that mode of x and mode of x is called, this is called norm or length of vector x. So it's as simple as that. So a normal vector space, a real inner product is a real inner product space is called as Euclidean space, and complex analog is called unitary space. So real inner product space is called a Euclidean space, and its complex analog is called the unitary space. So complex space. So any inner product in complex space is called unitary space for times to come. And if there are unitary spaces, unitary spaces, maybe in Cn. So we can write if x is zeta 1, zeta 2, so on and so on and so forth. Y is zeta 1, zeta 2, so on and so forth. Then xy can be written as xy can be written as so any unitary space Cn, x is 1, y is 1, so xy is zeta 1. So one of them has to be complex conjugate. It has not to be, then only you can define. So there is a difference between real space and complex space. In real space, both of them can be, but in the complex space, one of them, the elements can be as conjugate of it's not n, it's conjugate, so it's like this. So if it's a space spanning some space, so you can write it as x of p, and this is the conjugate part of it, conjugate of this p. So this x and y, they span some the integrand. That integrand is between some. So if it's from origin to some element, maybe 1. So in that space, one it's one element, and the other is a conjugate of the other element. And in unitary space, the properties can further be defined as in unitary space. It's first, second, x of alpha y1 plus alpha y2 can be, so it's here it's alpha bar x of y1 plus alpha bar x of y2. Alpha bar alpha 1, this alpha 2, this alpha x of y. So this describes the terminology. This expression is sometimes used to describe the properties of first, second, and the third. Third is which? Second and so accordingly, the terminology of xy. So that's why it's the complex. it's not normal, it's complex of this conjugate. So it's in a sort of Hermitian. So we can have x1 can be Hermitian symmetric is the term we are using. Some, and it's also conjugate. So if you remember, the properties of bilinearity are involved here. How we define the properties of bilinear functions. So that's why we say it's bilinear, but it's conjugate bilinear. Conjugate bilinear. And also, since it's one, so this is 3. So, and the norm is always greater than or 0. It's always positive definite in that sense. So that makes it slightly. So how we can characterize this unitary spaces or complex vector spaces? They have these 3 properties. It's Hermitian symmetric, it's conjugate bilinear, as well as it's positive definite. Apart from how we define these, technically. So these are the properties of complex vector spaces or unitary spaces. Now we are coming to our thing back to how we define the orthogonality, which we started, and a sister term called orthonormality. So how we define orthogonal and how we define orthonormal in this sense. So orthogonality is by definition if x and y are orthogonal if x of y is 0. And the relation is symmetric if x of y is so if it's symmetric, if we flip these elements x, y and y to x, but the complex conjugate of it. The symmetry is involved. So if the angle between them, if the cos of angle between them is x, y, cos of this alpha, beta or x, y. So if it's 90 degree, means cos of 90 is 0. So it will be angle between them will be between two of these spaces will be 0. Or there are 2 subspaces will be 0. So 2 subspaces are orthogonal or rather cosine of angle. So if 2 subspaces are orthogonal, if the angle between them is 0. Or every vector, if the angle is 0, every vector is orthogonal to other vector. That's why the angle between them, the product, it will come out to be 0, the product will vanish. That's why. So every vector, if the angle between them is 0, then every vector is orthogonal to every other vector between 2 subspaces of a given vector space. And now here comes orthogonality or as a condition. Now we have orthonormality. So either xy is 0 or xy can be 1. So we are again coming to our previous, the way we had Kronecker delta in the set. In that sense, you have either x may not be equivalent to y, or x is equivalent to y. And if x is finite, maybe x1, x2, so on and xn, then xi, xj is delta ij. This means if x is not equal to y, then it will be 0. And if x is equal to y, it will be 1. So you have orthonormality condition between two vector spaces can be defined in this manner. That if the product of two vectors, if one vector is not equal to another vector, its product, inner product, it will be 0. In case of other, it will be 1. So this defines the and we have an important property is that the number of vectors in orthonormal set is always finite. Not greater than linear dimensions of space. And orthogonal dimensions of space as largest number of orthonormal set can have. So the important thing is that the number of dimensions of these subspaces in which we define this inner product for this orthonormal condition, it's not necessarily that the number of dimensions is equal to the number of elements of that set in case of orthonormality conditions. So number of orthonormality is complete orthonormal set it's not necessarily it will be a complete orthogonal set. Because here, since we are interested in dimension 2, that becomes n for our cases, but it's not necessarily that the same. The number of dimensions is equivalent to the orthogonality, this orthonormal, for the orthonormality condition. It may or may not be same. The number of dimensions may not be the same for this, for a completely orthonormal set. So it's the beginning of how we define orthogonality and orthonormality in some simplest sense. Maybe I forgot one. You can also write if it's 0, so alpha I, xi, x. You can also write it like this. If you want to write it in terms of this Kronecker delta I. Delta I. If I is equal to g, or I is not equal to g, or it's small or it's 0 for orthonormality condition. You can write it symbolically like that. So this was a brief sort of how we define orthogonality, orthonormality. But the important point to mention is we are doing these operations in this complex space, C2 space. And the important thing is if you define one vectors as the alternate set of vectors have to be defined the conjugate or complex space, conjugate space. That's why those three conditions are there. It should be Hermitian, bilinear, conjugate are satisfied. So this defines this is an introduction to orthogonality and related things. So stop this class.